Okay, so today we're going to study a classic random variable called the exponential distribution. It's a classic random variable that's used to model a random time. So you can think of this as some random clock that goes off at a random time and rings. So if t is distributed exponentially, then we'll write it as such. And now the parameter lambda is called the rate, and it's a positive number. And we'll see a little bit later what the interpretation of it is, but it's kind of how fast the clock runs, the random clock. And to calculate the probability, so the probability that t is in between a and b, so we could write it this way, or we can write it like this. So it really doesn't, the point I'm trying to make here is that it doesn't matter whether we make it an open interval or closed interval at either end. It's always the same thing because this is a continuous random variable. Well, the probability that t is in the interval ab, that is to say that t is greater than a but less than b, is just the integral from a to b of the PDF, the probability density function f of t of the exponential random variable. Now for the exponential random variable, the PDF, which again we're denoting f of t here, is lambda e to the minus lambda t. All right? And again, lambda is called the rate. All right, now, again, so let's actually do this calculation now. So we'll calculate the probability that t is in the interval a being, and we just write out the integral. And now that's an integral we know how to do. It's exactly minus e to the minus lambda t evaluated at a and evaluated at b. And then if we do that evaluation, they just switch order because of the sign, and that's what we get. All right, and before we go any farther, let's just make sure that everything makes sense. This is a positive random variable. That is to say that it gives probability 1 to the interval 0 to infinity. So to see that a goes to 0 implies that e to the minus lambda t goes to 1. And if b goes to infinity, that implies that e to the minus lambda b goes to 0. So, just as I said, the probability that t is in between 0 and infinity plus infinity is actually equal to 1. All right. Now, let's just get a few facts about the exponential random variable. So, the first fact is just that the expectation, that is to say the mean of an exponential random variable, which is just calculated using the standard formula, there we go, is just equal to 1 over lambda. So that's an easy calculation to do. All right. And similarly, the variance is equal to 1 over lambda squared, which of course implies that the standard deviation is 1 over lambda. Now, to calculate the standard deviation, we need to just use the standard formula for the variance, which is the second moment minus the square of the first moment. So, both of these integrals are doable, and I think we'll study how to do them in a homework coming up. And so let me just write out the second moment here. And I'll give you a hint. The trick to doing both of these is to think about doing integration by parts. So both of these integrals you do by integration by parts, but I won't do that right now in front of you. I'll leave that as an exercise. Okay? All right. Now we're going to come to one of the kind of most central properties of the exponential random variable. That is the fact that it is memoryless. Okay? Let's say it has no memory. So knowing the past of an exponential random variable doesn't tell you about its future. So okay, that may sound a little bit philosophical or oblique. What I really mean by that is that if I ask what's the probability that the random alarm clock goes off at t plus s, time t plus s, given that I know it hasn't gone off before t, so capital T is bigger than little t, what's that probability? Well, that's just the same as saying at the beginning and saying the probability that it goes off in time s. So here we are, we have the time interval, and we know that it hasn't gone off in the hash part, and we want to know if it goes off in this remaining part. But since this remaining part is just of length s, that's just the same thing as asking if it had started from the very beginning and gone off in an interval of length s. So That's this conditional probability. This is called memorylessness, because if you're sitting at time t and you want to know what's the time it goes, probability goes off in the next couple seconds, in the next as seconds, then that's just given by t greater than s. So let's go ahead and show this. So we're just going to use the definition of the conditional probability. We just write that out. So that's the probability that t is greater than t plus s and t is greater than little t, divided by the probability that t is greater than little t. Okay? All right, now the numerator here simplifies, because if the probability that t is greater than t plus s and at the same time it's greater than t, the second condition doesn't matter because we already know it's greater. We're already asking if it's greater than t plus s. So that can be just simplified to the probability that t is greater than t plus s. Okay? And now if we divide that by the probability that t is greater than, that should be, yes, t plus s divided by e to the minus lambda s. Of course, I meant to write t here, so let's fix that. I meant to write t here, and then I meant to write t over on the other side. But just continuing on, that's just e to the minus s. All right. So now let's come to the last thing I want to talk about, which is the interpretation of the parameter lambda. What does lambda mean? Okay? What does lambda mean? Well, I already called it a rate, so it's the rate. So it's the rate at which this random variable rings, this random clock. So it's the chance at any interval of time it rings. So to see that, let's calculate the probability that t rings before t minus delta, given that it hasn't rung before t. So we're conditioning on big T being greater than little t, and we can of course write that as just 1 minus the probability that big T is greater than t plus delta, given that it's greater than t, little t. And of course now we just use the memoryless property. So we write the probability that t is greater than delta. And this is just the memoryless property. And if we now write out the formula that we calculated just a moment ago, it's e to the minus lambda delta. And now if delta is very small, we can use Taylor's theorem to approximate the exponential. So that's 1 minus e to the minus lambda delta plus 1/2 lambda squared delta squared. That's just Taylor's theorem. Keep going, dot, dot, dot. But if, since delta is small, we'll just neglect all the squared and higher order terms, and the ones cancel, and we get just lambda delta, which just means that since delta is a time, right? So it's a time interval, a short time interval, and lambda just gives the chance per unit time that the clock goes off, that this random clock rings, okay? All right, so of the random clock ringing, all right? And that's why this is the parameter lambda. And if that feels like the exponential like the Poisson distribution, stay tuned, that's coming up next.